So here's the first problem. So it says the graphs of functions f and g are shown in the figures above. Which of the following statements is false? The limit of f of x as x approaches 1 is equal to 0. So if I look at f of x, the limit as we approach 1, we have this jump discontinuity here. What's the limit though? Still 0. So this one looks like it's true, right? That's not what I want. The limit of g of x as x approaches 2 does not exist. So if I look at 2, that's going on there. So that one doesn't exist, I agree. The limit as x approaches 1 of f of x times g of x plus 1 does not exist. Whoa, Billy, what the heck is that one saying? So basically, if we're looking at the limit as f approaches 1, that's 0. And this would be the limit as x approaches 2. So what are we going to say here? 0 times does not exist, huh?
Wait, but isn't it as like it approaches 1 times?
Well, it's going to, but if you do like a direct substitution, that's going to be g of 2.
Oh.
Right, because it's x plus 1. I'm not really sure what to say about that. Let's move on. Since it's a true or false, maybe this one will be process of elimination for me, right? As x approaches 1 of f of x plus 1, so that's what, like here or something, right? And then g as x approaches 1 is like there. So that one seems like that certainly exists, right? Which one do you think we should pick as our answer, as the false one? I think so too.
So it does exist.
0 times does not exist is apparently does not exist.
So
Yeah, I think it's 0. Okay. Moving on to this one, the graph of f is shown above. For which of the following values of c does the limit of f of x as x approaches c equal 1? So let's see. I would start just by like, I'll use this. So here's like y equals 1 right through here, right? It's me trying to draw a straight line. It's hard. So it looks like there are 3 possible candidates, right? So here, here, and here. Everybody agree? At -2, does that work?
Yes.
Okay. So one of these 3, right? At 0, does that one work?
Yes.
Okay. Does 3 work?
No.
So we had eliminated that one and that one. So it has to be C then, right? Everybody agree? Okay. If I'm doing something you're not sure, holler at me. Okay, we're just kind of talking through. The graph of the function f is shown in the figure above. The value of the limit of sine x of f of x as x approaches 1 is well, I know that we can say this, right? And it's okay to do that because I know sine is continuous everywhere, so I can do that. What is the limit as x approaches 1 of f of x? 2. should be sine of 2. And if I fire up my calculator and type that in, what mode should I be in? Radian mode for AP Calculus. Sine of 2 is not one that you should know. 0.909. Whoop. The table above gives values of f at selected values of x. Which of the following conclusions is supported by the data in the table? The limit of f of x as x approaches 2 is 10, is infinity, or the limit of f of x as x approaches 10 is 2, or infinity. So if I look at here, I'm looking at the x values. Look like we're approaching 2. So right away, C and D are out of there. If I look at the y coordinates, oops, not those y coordinates. Those y coordinates were settling down towards 10. So that should be A. Everybody feel okay doing these? I don't think any of these are too bad yet. Probably that first one was the trickiest one because it was like, which one of these is not true? Those are always kind of tricky. Next one says the table above gives the values of f at selected values of x. Which of the following conclusions is supported by the data in the table? So I'm looking at the same thing. Okay. My x is approaching 6. So, well, that doesn't eliminate any of them. And my y is approaching a different value from the left and a different value from the right. So I should say does not exist. The table above gives values of the function f at selected values of x. Which of the following conclusions is supported by the data in the table? Okay, if I look at the same thing, we're heading towards 2. Okay, well, we have stuff about 2 and then 2 from the left. And I think 2 from the right. I can't. No, they're both lefts. Oh, yeah, lefts and rights. Okay, yep. So that doesn't help me a whole lot, other than knowing right away that those two are out, because the limit at 2 does not exist. So let's look here now. This is really just checking to know if you remember the notation for left-hand limit and right-hand limit, correct? So if I'm approaching 2 from below, we're heading towards -1. And if we're approaching 2 from above, we're heading to 6. I want that one. Let f be the piecewise function defined above. The value of the limit of f of x as x approaches 2 from above is 7, 9, 11, or non-existent. So which piece of my piecewise function do I need to be looking at if I'm looking at the limit as x approaches 2 from above or from the right? Yeah, exactly right. So this would be the same thing just as the limit as x approaches 2 of 4x plus 3, which when I do a direct substitution is 11. So I should pick 11. The table above gives selected values and limits of the functions f, g, and h. What is the limit as x approaches 3 of h of x times 2 f of x plus 3 g of x? Well, using our limit laws, we can say that this should be the limit as x approaches 3 of h of x times 2 times the limit as x approaches 3 of f of x plus 3 times the limit as x approaches 3 of g of x. So when I substitute these in, I know that the limit as x approaches 3 of f of x, or I'm sorry, h of x is what I want first, is 2. The limit as x approaches 3 of f of x is also 2. And my limit as x approaches 3 of g of x is 8. So I have 2 times 4 plus 24, which is 28 times 2, which is 56. Tessa? Well, it's to trick you. It's trying to trick you into thinking you need to do direct substitution, but you don't know that these are continuous. So you don't know that I can just do the limit by doing a direct substitution. They're trying to give you enough to be like, oh, well, this is just going to be, h of 2 times 2 times, or h of 3 times 2 times f of 3 plus 3 times g of 3, because I'm just going to do a direct substitution in this. But you can't do that because you don't know that f, g, and h are continuous. And in fact, you can see from the information that only g is continuous at 3. The other ones you can see are clearly not, right? Because g is the only one that evaluates to the same quantity as the limit. Elena? Okay, Braden? Of why, of this stuff? Yeah, so they give you that information on the left, trying to trick you into thinking like, oh, I'll just do this limit by doing a direct substitution. But you can't do that because you don't know that you have continuity at 3 for f, g, and h. In fact, the table does give you that information, right? We can look here. Since these two are different, you don't have continuity at 3 for h. You don't have it for f. You do have it for g, but because you don't have it for all 3 of them, there's no sense in, like, you don't have continuity at 3 for the composite function there. So it's trying to trick you into doing a direct substitution when you can't do that for this problem because you lack continuity at 3. Is that?
Yeah.
So you really needed this piece, and you need to use your limit laws to justify that or whatever. But very tempting to just want to direct substitute and go ripping and rolling. I think that 120 or something is what you get when you do the direct substitution. So they even give you the possibility of an answer that's not the answer you want. The next one says if a is not 0, then the limit as x approaches a of x squared minus a squared over x to the 4th minus a to the 4th is. So obviously if you do a direct substitution here, you get 0 over 0, which is bad news. So you know you can't do that. So the trick here is that you should recognize that denominator as a difference of 2 squares. So you should be able to do that. Reduce those things out. And now if you do a direct substitution, everything is fine. You should come up with B. All right. this is a long one. Let g and h be the functions defined by g of x equals negative 2x squared plus 4x plus 1, and h of x equals 1/2 x squared minus x plus 11 over 2. If f is a function that satisfies g of x is less than or equal to f of x, which is less than or equal to h of x for all x, what is the limit as x approaches 1 of f of x? When you see something like this, what should be screaming at you, going off in bright red letters? Squeeze theorem. Great. So all we're going to do is we're going to check the limit as x approaches 1 of g of x and of h of x. If they give us the same value, then that's the limit of f. If they're different, you can't say. So if I do this for g, what do I get? I get negative 2 plus 4 plus 1, just doing a direct substitution. Better check this one, though. So that gives me 1/2 minus 1 plus 11 halves. So that's, what's that? 6, 5. So they're not the same. I don't know what the limit of f of x is. You can give me enough information. I can't do it. Everybody happy there? Here we're told that f of x is the function x squared minus 25 over x squared minus 29, and g of x is the function x plus 5 over 2x plus 4. If h of x satisfies f of x is less than or equal to h of x less than or equal to g of x for x less than or equal to 1x, or 1 is less than or equal to x less than or equal to 5, what is the limit of h of x as x approaches 3? Again, you see this, we think, squeeze theorem. Does this matter? Only so much as that 3 better lay in between it, right? As long as the thing that the limit is approaching is inside that interval where the inequality holds, it's fine. The inequality doesn't have to hold everywhere, just around the neighborhood of what your limit is. That's enough. So we'll do the same thing that we did before. So if I do that, what is that? It's negative 16 over negative 20, so 4/5. Again, I'm doing a direct substitution because these are continuous everywhere near the dome, or, you know, around where I'm evaluating what the limit is. Obviously not continuous everywhere, but I don't need that. I just need continuous near what I'm looking for. So 8 over 10, also 4/5. Bingo, bango, got what I need. Elena.
On a scale of 1 to the AP test, where would this fall?
These are AP caliber questions.
So like when they do like the really easy ones at the very beginning.
I think for a lot of students, the limit stuff we're doing right now is some of the harder things to do because it's really theoretical. It's not computational. It's not algebraic. It's unlike the stuff that you have a lot of comfort with. It's very like, I have to think about this, and it's all new. When we start pushing symbols around, when we start talking about derivatives, things become more familiar feeling because it's like, oh, this feels like an algebra problem now, or this feels like a, something I'm a little bit more comfort-wise, familiar with, but this is very unfamiliar right now. And as a result, sometimes feels like the hardest stuff. So I don't, like easy, hard, I don't know. Like, I don't, aside from that very first one, I thought that none of these were absurdly tricky. But if they feel hard, that's okay. Like, I think that sometimes the stuff we're doing right now is kind of the hardest stuff you do.
Yeah.
Well, again, here's what I'll say, and this is speaking to a group of people that are probably going to take a lot of math courses at some point in their life. When you start a math course, it is like a new branch of mathematics. Like, it's your first time taking a calculus course. It's your first time taking a differential equations course. It's the first time taking a linear algebra course. It's going to start off and it's going to feel very, very hard. And by the end, you're going to go like, why did I think that stuff in the beginning was that hard? This is actually pretty straightforward and it's actually not bad. But you don't feel that way in the moment. In the moment, it feels hard because it's all new. And what you're feeling is just not hard, it's unfamiliar. And you're trying to get your head around the unfamiliarness. Because it's a new set of ideas that you have to get comfortable with and build some intuition for. Once that happens, things feel much, much easier because things start feeling familiar and the answers are kind of what you'd expect because you now have some intuition to draw upon. The problem is, like high school, everything has kind of been the same aside from geometry. And even geometry, a lot of the big ideas there you saw in algebra and pre-algebra, like the Pythagorean theorem, things like that. It's like areas and volumes. Like, these are not new ideas to you. Like, the proof stuff was hard because it was unfamiliar. The actual idea of these things is not that difficult because the theorems are pretty simple and pretty straightforward. But like, doing that was really unfamiliar and felt really hard in the moment. And by the end of the course, when you went back and tried to do the theorem or the proofs from the beginning, it was like, this is really easy. I don't know why I thought this was so hard. And it wasn't that it was hard, it's unfamiliar. And that's what that's what you're feeling right now. And like, that's perfectly normal as a math student. You'll always feel that way unless you're like generationally brilliant. And even like generationally brilliant students still, when they encounter something new, need that time to like build some intuition out, eventually. Okay. So again, we'll continue to do multiple choice practices. Prior to you may have seen, I put on my Notre Dame. So I have some other AP practice stuff that I'd like you to do prior to your chapter test. So I have some stuff in here to look at, I think, as part of like your test review stuff. After what we talk about today, there's really, aside from the things I tell you to skip or don't worry about, because these progress checks are built in a way that like, where I'm putting my test is not where the AP is like stopping their, they have some content in there that we haven't talked about that we will, but where my test is landing is, I can't, it just has some stuff in there. It's like, that's a term we haven't talked about. We'll do it. It's actually 2.1 that we'll be talking about, but I think 2.1 serves as a better transition into talking about a derivative than it does all this limit stuff, because it's kind of like you do this limit stuff and then you go away from it. So there's like some free response questions in here, and there's some multiple choice questions. Yes, sir.
You are talking about one practice level one.
Mm-hmm.
You mean level 2?
Yes, I do, of course. Yeah, let's fix that. That's got to be what I meant there. It's probably I cut and pasted it so that and then I forgot to change the number on that. Yes. Okay, thank you. Gigi, of course. Page 9/5/23. Do you want to do some questions here from homeworks? I know we haven't talked about a couple of the stuff from later on in this 2.5. Pierce?
55A.
55A? Yeah. All right. So prove that the equation has at least one real root. So I'm going to start by moving everything onto one side. I'm going, and it doesn't really matter which side you move it all onto, but I'm going to move the trig thing over. And now what I want to do is I need to find, well, I can argue that this is continuous, right? Should do that because I'm going to be using the intermediate value theorem to prove that there's a real root here. So I need to have continuity. So my explanation here is I know that x cubed minus cosine x is continuous because it's the difference of two continuous functions, a polynomial and a trig function respectively. So I have that. Now what I want to do is I want to find an interval of x's where, like an interval a, b of x's, where f of a is negative and f of b is positive. I don't care how big that interval is, but just finding an interval where the function changes from negative to positive or positive to negative would tell me that it has to cross the x-axis there, and that's going to be my justification for a real root. So I can see right away that f of 0 is going to be, what's cosine of 0? It's cosine of 0 is positive 1, but this evaluates out to negative 1, yes. So there's my negative piece. And here's what I'll do for my positive. I know that cosine's smallest value could possibly be is negative 1. So I'm just going to do f of 2 because that's going to give me 2 cubed, and there's no way that cosine of 2 can get me a number that's not positive here, right? So this is greater than 0. That's enough, right? So I know that since negative 1, which is f of 0, is less than, or I think it's just less than 0, which is less than f of 2, the intermediate value states, or theorem states, there exists a c on the interval from 0 to 2 such that f of c equals 0. That's my one real root. At least one. Could I do this more times? Sure, possibly. Who knows? I bet if we went and looked at the graph, there's probably more than 1 0 for this, but I don't know. Tessa, you're making faces. Such that is just my abbreviation. That's a comment. I did not actually have to find it. Part B says use your calculator, to really zoom in enough that you can find like an interval that's like this short, has a length of 0.1 that contains that value. And you could have on your calculator graphed the two sides and found the intersection, actually found the value of x. But we don't. What if this was a no calculator problem, right? Everything I did here did not require a calculator.
But even for the F2, you don't have to find that.
I just know that it's positive. Yeah, all I need to know is it's greater than 0,
Okay.
which is enough because that's going to tell me that I have something less than 0, something greater than 0. There's my interval. Isabel?
So for like the f2 part, you just chose any number that's like greater than 0.
Well, one I would be concerned about with the possibility of it being like, I guess it couldn't be less than 0, right? And I know cosine of 1 is not 0, so I guess that would probably be fine. Yeah. Yeah. When you say any number bigger than, decimals might be a problem.
Like any whole number.
Yeah. Like a half. I think anything greater than 1 maybe is the better way. You know, like all those decimals in there would be less than 1 would be potentially problematic. But I don't know. I mean, you'd have to check them. But I didn't want to have to do it, break out the calculator if I didn't really have to. And since it doesn't specify like the size of the interval that you're looking on, I don't care how long this thing is. I just need, you know, I could have used 200,000 as my other x, and it's like, okay, good enough. I mean, it's a pretty dumb one to pick, but like, okay. Does that feel good, Pierce? Yeah. Okay. So again, at any point, if you're being asked to like show something, like show there's an x that exists that gives you a specific y value, that is an intermediate value theorem problem. That is your tool. If you want to show that there's an x that gives you a specific y, that is your tool. And the big piece you have to remember is you need continuity to use it, so you have to show that first. If you don't have continuity, that doesn't have to hold. It might, but it doesn't have to. Tessa. 18. I'm going to put 17 on there too, just so I don't have to do 2 screen caps to get the directions with it. So it says, explain why the function is discontinuous at the given number a, and then sketch a graph of the function. Okay. So what I'm going to do is do the limit as x approaches -2 from the left of f of x, and the limit as x approaches -2 from the right of f of x. So when I do that, well, I probably don't need to write f of x here. I could just write 1 over x plus 2. It's good enough. Okay. When I do a direct substitution, if x is a little bit less than -2, the denominator is going to be a very, very small negative number, right? A negative number that, I shouldn't say very, very small. I should say negative number very close to 0. Everybody agree with that? When I divide by a number that's very, very close to 0, what do I get? A big number back, right? So I'm dividing by a number very close to 0 that's negative, so my result is going to be a really small negative number, right? This is giving me like negative infinity, because I'm like dividing by -0.0000001. So you're getting like, you know, -1 times 10 to the 25th or something, you know, something absurd, you know, gigantic, or really very, very negative number. The same thing is going to happen over here, right? If I'm looking at a number to the right of -2, but still very close to -2, you're looking at like 1.999999999999999. When you plug that in, you have a number that's very close to 0, but positive. So this one goes to positive infinity. So we can say then the limit as x approaches -2 of f of x does not exist. And that'll be enough right there to say that, to show your discontinuity, because to show continuity, you need the limit. Boy, that was some bad penmanship, Mr. Kulik. As x approaches -2 of f of x to equal f of -2. Well, if this does not exist, well, this is just 1, right? So like clearly you got it. As soon as you have a does not exist for the limit, you can't have continuity there. Does that feel okay, Tessa? You didn't like this because I didn't actually do any algebra, did you? I just had to like kind of think about what's happening numerically. So if we draw the graph, that's the second part of this. What's this going to look like? Yep. So that's your picture, is you'd end up with something like that. So what I did was I kind of did or thought about this like a direct substitution. So if I'm looking at something to the left of 2, I'm thinking about like that number as my substitution, right? When I plug that in, I'm going to have 1 over -0.0000001. So when I do that division, I have like -1 times 10 to the, 15th or something, right? So that's what's sending to -infinity. Every time I add another 0 onto the decimal, it's adding another like power of 10 into my exponent. So the closer I get to -2, without actually getting to -2, I'm just adding more powers to that exponent, but it'll always be a negative number. And then similarly here, I'm thinking about this as like -1.99999999999999999. So when I do the direct substitution, I'm always going to end up with a positive value, but very close to 0. So when I do the division, I end up like 1 times 10 to the 15th or whatever, which is my proxy for positive infinity.
Wait, it's not just enough, it's direct substitute. It doesn't exist because the denominator is 0.
Nope. Because here's the thing, Pierce, if this was like 1 over x squared plus 2, they would be going both to positive infinity, which the limit then should be infinity, but it wouldn't agree with, the limit exists, it's infinite, but it doesn't agree with the evaluated f of 1 or whatever, f of -2. So like it's a different reason that it fails that time. Is that?
Yeah.
So it's just kind of, you have to, it's subtle, but Elena.
Answer 17 and 18 both with this explanation. Oh no, you can't, because never mind actually. It does not apply to
It's still the same reason for 17 though, because the limit doesn't exist.
So you could answer it like that.
Yeah.
Okay.
Yes, 100%.
And then so if one of the limits doesn't exist, you can automatically say that it's just because that all.
Well, a left-hand limit or right-hand limit is always going to exist, unless it's just like not there, right?
Then how does this not exist?
Because the left-hand limit and the right-hand limit disagree.
So then.
That's why the limit doesn't exist at -2. But if you have like if you take a left-hand limit and a right-hand limit, those like exist. Even if the overall limit doesn't. Rita?
For number 17, I feel like that the function is like undefined at -2, would that also be like an exception?
Sure, yeah, if you say that like, well, you know, f of -2 is undefined, can't have, you know, like you have to have f of whatever, f of -2 has to evaluate out to some finite number to have continuity there, right?
Yeah.
So that would be fine. And the next one's like, oh, well, you can't use that argument,
Yeah.
but you could still use this limit argument in either, and that's okay. Last call on 2.5 stuff. At least for today. You can always come back and ask more later, you know. But we did, I think we had hit a lot of these last time. Okay. Let's start talking on 2.6. In 2.6, we're going to start looking at limits at infinity. So you're going to be looking at situations where the limit of f of x as x approaches infinity or negative infinity. We're going to be looking at how to do that, because no longer is direct substitution going to be an option. If the limit is approaching infinity or negative infinity, you can't plug infinity in like a number and grind through that. That's not how that works. So we're going to have to be looking at taking some different approaches. Now, there's lots of different ways that a limit can approach, or going to infinity can approach a finite value. If I look at this first one, it's kind of approaching that finite value from below. Here, the function is approaching that finite value from above. And here it's oscillating, but each time it oscillates, that distance to that finite value is getting closer and closer and closer. So it can approach from both above and below at the same time. That's like a dampened, like trig function, like a dampened sine function or cosine function is what you're looking at. Where each time, like the amplitude, every period, the amplitude gets a little bit smaller. Eventually it's settling down to that same value, but it's coming at it from both directions. Isabel?
For like the definition, is it x approaching
X approaches infinity.
a?
Yeah. Yeah, that's this whole section is going to be about what do we do if we have a limit where x approaches infinity or negative infinity? Like, what can we do with that? So that definition 2 is just the same definition as 1, and just we've replaced positive infinity with negative infinity. Whoop-de-dee-doo! And then definition 3, we define a horizontal asymptote.
Yes.
So we say that if our limit that goes to a positive or negative infinity exists, and it's a finite value, then that finite value is our horizontal asymptote. So if we go back and we look at these 3 examples above, we'd say that like y equals L is our horizontal asymptote, which matches kind of what we had said in our algebra 2 class or trigonometry class, that I think we used the broader term end behavior often to describe that sort of situation, but we're going to call these now horizontal asymptote, and this is our definition for like how you'd prove something as a horizontal asymptote. Is you just need to show the positive or negative, or the limit at either positive or negative infinity is that finite value L. Which before, what did we do in algebra 2 or trigonometry? Just looked at the graph and like, it looks like this, which is not very satisfying as a mathematician, right? Okay. So couple of like identities here. So what I wanted to do here is just give us an example of, this is a curve that has two different horizontal asymptotes. So this is the function tan inverse. Remember, if we graph like one period of tangent, we have a vertical asymptote at negative pi over 2 and at pi over 2. Right, where it looks like this. So if we find its inverse, those vertical asymptotes become horizontal. And we can reflect our graph about the line y equals x. So our graph now kind of looks like that, where we see horizontal asymptotes at negative infinity and at positive infinity, but different asymptotes, right? I know I just threw a whole bunch of algebra and trigonometry back at you, and if you're like, whoa, slow down for a second, that's okay. I'm going to take a deep breath right now. So we just used like general things about inverses, a lot of asymptote definitions and nomenclature, and you know. All right. Let's look at an example here. So here we're given this graph, and we're asked to find the infinite limits, the limits at infinity, and asymptotes for the function f. So when I say infinite limits, what do we mean here? We're looking for situations like that, where the limit is equal to positive infinity or negative infinity. Limits at infinity we're looking for a situation like that. Everybody okay? Okay. So let's start writing these down. I'm going to erase this stuff real quick. Is that okay? Okay. I just wanted to remind us the difference between those two different phrases were, because well, they sound so similar, right? It's easy to kind of get mixed up. Okay. So let's do our infinite limits first. Do we see any? Yes, right? Looks like here, the limit as x approaches negative 1 of f of x is equal to positive infinity. And then again here we have, so how am I going to do this? Yeah, that's the negative infinity. And then when I do it from the right, that's the positive infinity. Great. So what does this tell us? Vertical asymptote at x equals negative 1. And then either of these would tell us we have a vertical asymptote at x equals 2, right? Either or, all of them, doesn't matter. Remember, our definition for a vertical asymptote was you just had to have one side of your limit is infinite. Could be both sides are infinite, that's fine too, like we have with negative 1. Okay. And then our limits at infinity. Well, does that one look like it's settling down to a specific value? Looks like 2, doesn't it? And then this one also looks like it's settling down. Oops. And what does that appear to be settling down to? Let's see, 1, 2, 3, 4. Yep. So this would say we have a horizontal asymptote at y equals 2, and that is our justification for a horizontal asymptote at y equals 4. Does this feel okay? Not a big deal, right? This looks very similar to the pictures we've interpreted before in a trigonometry algebra 2 class. We're just adding this limit notation on top of it. Elena.
Have the horizontal asymptote at y equals 4, even though it cuts through y.
Yes.
Okay.
Yes. So no longer are we defining our asymptote or horizontal asymptote as a line the graph approaches but does not cross. It just means as it approaches, it just has to approach that line from like at infinity or negative infinity. You're just looking strictly at the end behaviorness. Because notice even we would count this thing up here where it's crossing infinitely many times on its way out to infinity would still count as an asymptote because the limit is still heading down to that value L. Because each time the amplitude on that is getting a little bit shorter. Yeah, so we need to kind of divorce ourselves of this approaches but does not cross notion, which works really well for vertical asymptotes. That still is fine way of thinking about those, but the horizontals, we need to change our mind now. All right. So what's going on here? We have the limit as x approaches infinity of 1 over x. How am I going to do this? Okay, we could graph it, or what else? I would use a table here. But yeah, we're defaulting back to those because our algebraic methods all require finite values that where x is approaching, right? So, maybe 10, 100, 1,000. So I have 0.1, 0.01, 0.001. What looks like it's happening? It's heading towards 0, right? Any values for my x? Yeah, more or less. I usually just pick them like getting, in a situation like this, getting bigger by an order of magnitude of 10, right? But you could have done 7, 254, 3019. It doesn't, why would you do that? I just pick these because it's easy to do the arithmetic in my head. So do the same thing this time, just with negative 10, negative 100, and negative 1,000. So what's happening here? We're heading towards 0 also. I'm just doing 1 over x. So I'm 1 over negative 10, 1 over negative 100, 1 over negative 1,000. So I'm just doing that quickly in my head. The decimal is going to be more meaningful to us than the fraction would be. So I'm just cutting right to the chase of the decimal. Does that feel okay?
Yeah.
All right. So this then is going to become a theorem. And notice that we're going to do this not just for 1 over x, but we're going to do this for 1 over x to the r. So if r is a positive rational number, then the limit as x approaches infinity of 1 over x to the r is 0. And the same thing holds if x approaches negative infinity, again, 1 over x dr approaches 0. So again, we have to have a rational number there. You can't have like x to the pi and use this, but you can use it for any radical of x, right? Because remember, radicals are the same thing as a rational exponent. Like the 4th root of x is x to the 1/4, which is lovely. Let's do an example. So here we have the limit as x approaches infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. So here's the trick that I am going to use. What's the biggest power of x in this problem? 2. And that biggest power of x occurs in the numerator or denominator? Both. Okay, then no problem. I'm going to multiply the top and bottom of this fraction by 1 over x squared. When I do that, what am I going to get then? Ooh, excuse me. Thank you, everyone. I would get this, right? Everybody agree? Why do I want to do that? Well, now if I use my limit laws, I can do this, right? Oops, forgot to write x squared there. Is everybody okay with the limit laws that I've used, where I distributed the limit everywhere, pulled the constants out front? I have pulled the 2 out front. Yep. Yeah. That's correct. It is 2 over x squared. This is the last one on top, but I pulled the 2 out front to just make it 2 times the limit of 1 over x squared. Now, if I use my properties, what's the limit as x approaches anything of a constant, or limit of any constant? The constant, right? What's the limit as x approaches positive infinity of 1 over x? 0. What's the limit as x approaches positive infinity of 1 over x squared? Constant, 0, 0, and I end up with 3/5. Jacob.
So is the limit for the second one, where it's just 1 over x equal to 0, just because it has like a vote 1?
Exactly. Yes. Yes, this falls into this theorem because in this case, r is equal to 1 if it's 1 over x. Yes, 100%. It doesn't have a name. Just theorem 5 is what we're calling it here. But it's like the backbone of how we do these infinite limit problems, is using that observation that if I divide a constant or really anything by something huge, it goes to 0.
If on like the AP test they were asking about this, what would I like write into
No, I would say that the work we've shown here would be sufficient for them.
It's 520.
Showing that you use the limit laws correctly, and then, those things going to 0, I think is fine. Remember, I want to connect this to something that we did in both pre-calculus and in Algebra 2. This is a rational function, right? Remember when we had those 3 set of criteria for how you find the horizontal or the asymptotes? The horizontal and oblique and other asymptotes for these? You looked at if the degree was equal, then it was leading coefficient over leading coefficient. What did we find the limit here was?
Oh my gosh.
The exact same thing, right? In fact, you've been using this technique the whole time and you just didn't really realize it, which is lovely because it's going to make it really hard to forget what to do now, right? Because it's connected back to something you've already been doing.
So do we even have to do the work, or so you were just?
You do, well, it's a calculus course, so I need you to use calculus to do the problem.
But we know what the answer.
But you know what the answer is going to be.
So if you get something different, so not the same thing, it's always.
Yeah.
Wait, what was it? When it was like, one was like
So
less than the
we're
other?
here to have.
We can at least get that.
Yeah,
And here's the thing, Elaine. Here's the great part. If it's a multiple choice AP question, it's a 10-second problem, which is great because now you can make up some time for something else you actually have to think about. Right? All right. Let's do another one. Uh-oh. Well, the vertical asymptote's easy, right? What is it? 5/3, right? And we could show that if we wanted to. I don't really want to. I'm more interested in the horizontal piece.
Because you set the denominator.
Mhm.
So that it gets it back.
Oh,
Yeah, you're just using what we learned from like Algebra 2 and pre-calculus about a rational function. We know that there's going to be a vertical asymptote at 0, provided that it doesn't reduce out. But I can see that like there's no reducing that's going to happen on this thing. How am I going to do this limit, though? I would not. Easier.
really?
Why do I need the square root around it? To put it inside the other square root, right? But down here, do I really want this square root there? So let's just make it, let's just evaluate the square root of 1 over x squared. They're equal, right?
Oh,
I square root of 1, which is 1. Square root of x squared, which is x. So now if I do this, what do we have here?
Would you recommend always trying to use 0 to 5 for finding asymptotes?
Yeah.
Would it be helpful anywhere else or mostly?
Well, you need a limit going to infinity to be able to use it. So if you're doing anything with an infinite limit, or a limit at infinity, I should say, it's probably going to come up, or we have another version of it for exponentials here that we'll look at in a minute. But those are going to be your main 2 tools. So again, I can use my limit laws now to just move some stuff around. So remember, I can sneak that limit underneath the radical, and that's okay. Oops, why did I write 3 there, dum-dum? I meant to put the 3 there and infinity there. And now, and can everybody see that if I do the same thing at negative infinity, I'm going to get the same value? Well, you have to be careful because it might have 2 different horizontal asymptotes, right? So I do need to take a moment and go, if I do I have to check the other one to make sure that I'm getting the same thing. And if they're different, that's fine. You can have 2 different horizontal asymptotes, as I showed you with the inverse tangent.
Yeah.
But you do need to, like, if it asks to find all the horizontal asymptotes, and you only do one of them, and there turns out to be a second, I'm like, oops a daisy.
Yeah.
But hopefully on this one, you can see that, like, even if I make this negative infinity, and I get to here, and I just replace everything with negative infinities, everything still goes to either constant or 0. The negative part doesn't have any impact on what's going on over there. Feel good so far? Okay. Let's try another. Yes.
On the bottom, it was where you apply the limit on it.
So you're looking over here?
I thought like there's a different rule for how you put 5 in front of the limit. I didn't know if you could do it like
Just a constant, like 5 over x is just same thing as 5 times 1 over x, right? That's, Jacob.
So if you check it at negative infinity too, would anything actually be different in the order?
No. I mean, other than like negative infinities being on your limits,
Okay.
but like nothing would evaluate differently, right? Because if I look at each of these, everything to this point would be identical work-wise, and every one of those limits is going to come out to be the same thing, right? It's going to go to 0 and it's going to go to constants. So
Yeah.
is that? And again, like if it's a situation like this, and I would just, I would just skip to this with the negative infinities and just write the answer or whatever. Like I don't think you need to do the extra step here because it's like clear if you've done it the first time that you know how to do it.
Okay.
You know what I mean? All right. Let's take a look at this one here. What do we think? So if we're going to do this, if you think about it like in like a direct substitution-y kind of way, it's kind of like an infinity minus infinity here, right? Because it's like infinity squared, square rooted, that's like infinity, but then it's minus infinity, right? Infinity minus infinity was one of those indeterminate forms that we can't do anything with. So there's got to be a different way of doing this. What does that look like? which should be screaming at you. Multiply by the conjugate. Because you have something squared plus or minus something not, under a square root. Plus or minus something not under a square root. Right? Everybody's okay? And you're thinking like, why would I want to make this like, it's going to give me a square root in the denominator? I'm like, yeah, it is. And that's okay. So I just went and FOILed out the numerator there quickly in my head. Everybody's okay with what I did there? Just using a difference of two squares factoring pattern, I was able to do it like instantly. Now I feel good, right? Maybe I'll write it this way.
Oh, wait.
And then when I use my limit laws, so what do I get here? I get 0 over 1 plus 0 plus 1. Just 0. Kind of a surprising result. We okay? Yeah. It takes some time to process, right? It's okay. I'm going to skip this next one just in the interest of time because I want to look at this. Here's your second tool. Remember when I said that, like there's a similar one for exponentials? This is it. The limit as x approaches negative infinity of e to the x is 0. Why is that? Why is that? If you think about this, it'd be the same as this, right? Instead of going to negative infinity, we go to like, oh, maybe I'll write this first, right? Everybody agree that that's equivalent? And this definitely has to be going to 0 because you have a constant over something enormous, right? All right. We'll stop here. I got a bunch of examples here to follow, but that's probably as far as we can get today. as something to think about, I don't want you to, don't worry about working on the homework yet. Actually, we'd put something here. Let's write it here. We will, but not next class. So let's think about ranking So when I say ranking functions by growth rate, so like, you know, let's say we have like trying to think, is there anything else that's kind of common enough to come up? I guess I could do something like that. Nah, that's good enough. So think about that for next time. This will be really helpful intuition for multiple choice questions if we kind of get to figure out a way of like ranking these functions by like which one's getting bigger faster. Yes, that's like the factorial symbol that you might remember from like your Algebra 1 or pre-algebra course. Remember, what does factorial mean?
Like 5 times 4 times 3.
Yeah. Yeah.
It's just so.
Okay. So again, we're not going to worry about the homework quiz for next time. I want to do more stuff first, but you guys can probably go like up through like 30 or 31 through the problems if you want to get a start working on things. That would be fine.
But do we have to miss this exam?
We'll do it after we finish the section, because there's some stuff at the end that I want to be able to do as homework quiz questions without like rewriting what's going to be on the homework quiz. Right. We'll do it, but after I finished this section, because I think like 2 or 3 of the problems are from things that we haven't gotten to yet, or I'm not sure. And I just, rather than like, I did that before where I stopped and they had to like, the stuff online didn't match the stuff in class, and then it was like a thing, and it was like, oh yeah.
Yeah.
So I'm just gonna stop here and we'll do it then.
Wait, should we do the ranking of the functions by growth rate?
That's not a homework, it's just something to think about. So just try.
Can I